Thanks a lot. Thanks for the invitation. I'm going to Europe in a couple of weeks, so this is a good preparation for me to get used to the time zones. So this is joint work with Nadia Lafreniere that has been ongoing for the last year, essentially. Right now, the paper is on our website, but it's being written, it's being polished, and I've deliberately kept the slides pretty long with a lot of related things and similar problems. There will be a link to the slides. I'm going to post it in the chat as well. Yep. So we'll probably not have time to go through everything. So whatever piques your interest, you can find this the PDF file and then look it up. So this is about the symmetric group algebra. We work over an arbitrary commutative ring, but it's enough to have. It's actually enough to work with the integers for most of what we're doing. Is the font size large enough? Okay, now I don't see your video well enough to tell whether that's a yes or a no. But I can increase it. So note that this symbol means that this is a fairly important thing compared to the other bullet points, which can be random observations. So in generally, I don't think I need to explain to you what a group ring is. I'm just fixing some notation. K bracket G is a group algebra of a group G over the commutative ring K. And if U is an element of this group algebra, there are two linear maps that are attached to it. One is L of U, which is left multiplication by U, and one is R of U, which is right multiplication by U. They're module endomorphisms, so they're linear maps. And so you can view them essentially as matrices of size G times size G. Most of the time, it suffices to study one of them, because if you view them as matrices, they are very closely related. So when K is a field, each element of Kg has a minimal polynomial, which is defined as usual. It's the smallest degree monic polynomial that annihilates the element. And actually, this is probably very basic stuff, but I couldn't find it written down anywhere. If K is the integers, then this minimal polynomial is also over the integers. So here are some more basic facts that probably should be exercises in most textbooks, except I haven't really seen them much. One is that left multiplication by U and right multiplication by U are conjugate as matrices. So this symbol means conjugate. However, only if K is a field and G is a group. Well, G is a group for us, but the K is a field property is probably important. Notice that there is yet another relation between L and R. I'm going to go briefly over this. The group algebra is not just an algebra, it's a Hopf algebra. It has an antipode map called S, which simply sends each element to its inverse, and otherwise is linear. And because of this antipode map, which is an anti-algebra homomorphism, you also have this conjugacy. L of U is similar to L of S of U if K is a field. And generally, L of U is similar to R of S of U. So the left and the right regular representation are isomorphic via this antipode. Okay, and by the way, most of this generalizes to arbitrary Frobenius algebras. So for now, we have been doing mostly abstract nonsense as the bit of linear algebra. So now let's specialize to the symmetric group algebra. N will denote the set of all non-negative integers, and bracket K will be 1, 2, ... K. The N-symmetric group is a group of permutations of the set bracket N. And its group algebra is a lot nicer than an arbitrary group algebra of an arbitrary group. In particular, when the field has characteristic 0, the group algebra has a well-known structure known as Young's seminormal form. So if you forget for a moment about also representation theory, it's just saying that the group algebra in this case is isomorphic to a product of matrix ring. the sizes of the matrix rings being these numbers of Setter tableaus. As a consequence, every element of the group algebra is conjugate inside the group algebra to its own antipode. Notice a subtle point. The left action, so L of u is always conjugate to L of S of u over any field. But u itself is not always conjugate to S of u, but it is when you have a group, when the group is a symmetric group and the field has characteristic 0. So this is actually a more general fact about so-called ambivalent groups. So groups where all elements are conjugate to their inverses. So, but the topic of this talk isn't really the group algebra of the symmetric group. It's specific families of elements in those group algebras. So this all was in a way background. Now I will define some basic notations for certain permutations. One of them is the good old K cycle. My notation for this is cyc I1, I2, ... ik. So this is the cycle that looks like this, and all the other elements are just fixed points of it. For k equals 1, this is the identity, because cycling one element just does nothing. For k equals 2, you're cycling two elements, so it's a transposition. And out of those transpositions, you can build the so-called Young-Jucys-Murphy elements, which I think everybody, well, most people here know, but they make for good background. Whenever you discover a new family of elements of the symmetric group algebra, I think it's always reasonable to compare them to Young-Jucys-Murphy. So the case Young-Jucys-Murphy element is the transposition of 1 with k plus the transposition of 2 with k plus ... plus the transposition of k minus 1 with k. And the first interesting theorem is that they all commute. MI is always MI. This is pretty easy to see. It's just multiplying transpositions. But a much less obvious fact is each mk has a minimal polynomial that factors into linear factors. It looks like this. It's basically the sum over x plus I, or x minus I, if I goes from minus k plus I to k minus 1. And one little question I want to ask, even so it's not related to our topic, is there a really algebraic proof of this, like without any representation theory or linear algebra? Because I've only seen proofs using some sort of eigenvector analysis. Nothing deep, nothing particularly advanced, but it's strange. It feels like there should be an induction. So at this point, there are books about Young-Jucys-Murphy elements. This is the famous one. There is another by Kleshov. There are a bunch more properties. One is because these elements commute, you can apply symmetric functions to this, and usually something interesting comes out. For the elementary symmetric polynomials, for example, you get the sum of all permutations with a given number of cycles. Another theorem due to Murphy is that the whole set of symmetric polynomials in the Murphys is actually the center of the group algebra. So speaking of all these families, it's good to have in mind a different way of viewing them. And that way is using card shuffling. So how does this work? You imagine a permutation as a deck of cards labeled 1 up to n, just shuffled into some order. The permutation determines the order. And a random state is a random linear combination of this permutation. So it's a convex combination of those possible orders. And the coefficients are understood to be the probabilities of how likely it is to be in a given order. Now, you can actually drop the convex means that the coefficients are greater or equal to 0 and their sum is 1. But you can easily drop the sum being 1 and just rescale with the sum. So, for example, this element of the group algebra corresponds to the random state where it's equally likely to be in the order 1 to 3 and in the order 2, 3, 1. This means that a random state is basically an element of the group algebra over the real numbers, except we require the coefficients to be non-negative reals. And an endomorphism of the group algebra is then a random shuffle. So it sends a random state to a random state, assuming that it doesn't give you negatives. So in a way, all these elements of group algebra, they generalize shuffling cards. For example, R of mk, so right multiplication by the case Young-Jucys-Murphy, means that you swap the case card with some card above it, chosen uniformly at random. So everything I say in the following about the group algebra of Sn, you can view this as claims about shuffling cards. Nadia, for example, thinks of things in this form. I usually don't, but it's a matter of translating between two languages. So back to the algebra. Here is another famous family of elements of the group algebra of Sn. These are the so-called k-top to random shuffles. This is the sum, so the case one is the sum of all permutation sigma, for which the numbers between k plus 1 and n appear in sigma from left to right. So sigma inverse is increasing when you restrict it to these numbers. In particular, B1 has this nice form, cycle 1, which is identity, plus cycle 1, 2, which is a transposition, plus cycle 1, 2, 3, and so on, all the way up to cycle 1, 2, n. The other BKs look a little bit more complicated if you expand them out. However, there are some interesting theorems found by Diaconis, Pitman, and Woloch. One of them is that actually each of these elements is a polynomial in B1. And B1 has a pretty simple minimal polynomial. It is the product of x minus I for all I from 0 to n, not counting n minus 1. That's a pretty fun fact with, at this point, quite a few different proofs. This is, in a way, the easiest way to prove it, goes through this theorem. And in particular, because all of them are polynomials in B1, they all commute again. And they're called random to top shuffles. They're called top to random shuffles because they take a random card and move it to the top of the stack. Or they're also known as settling libraries. And their antipodes are called random to top shuffles for a pretty similar reason. There is a much more complicated variation of this shuffles, which is the so-called random to random shuffles. In terms of card shuffling, they're very simple. You take a random card and you move it to a random place. Algebraically, it is the sum of all permutation sigma multiplied by the number of so-called non-inversions of length n minus k. So the number of n minus k elements of, n minus k element subsets on which the permutation is increasing. So if n minus k is 2, these are 2 element subsets. So these are the pairs of numbers on which sigma is not, which are not inversions of sigma. That's the name. It has been proved in a pretty painful and long way by Reiner, Salioli, and Welker that these n plus 1 elements are 0 up to Rn all commute. So one of the if you ask me, one of the pressing questions in the subject is actually finding a readable proof of the theorem. There are 2 proofs now. One of them is by Reiner, Salioli, and Welker, and the other is by my co-author Nadia Lafreniere, and both of them are long. Both of them seem to be like missing the mark. There seems to be some reason why they commute, but nobody knows why. And again, the minimal polynomial can be found. Or more precisely, this polynomial annihilates this R1. You have similar polynomials for the other R's, which are more complicated. And this, again, the proof of this at this point is something like 70 pages long. It's very strange that nothing simple has been found. This is a result of Lafreniere again. The proof uses a lot of standard tableau theory, Young semi-normal basis, promotion on tableaus and evacuation and derangements. A lot of things going in there. I'm also wondering what subalgebra of the group algebra is generated by these R's. Here are the dimensions for the first values of n. It doesn't seem to grow all that fast compared to the whole symmetric group algebra. But I don't know, maybe knowing n up to 6 is not enough. And actually, you can write the R's as products of the BKs with their antipodes. It's basically saying if you want to do a random-to-random shuffle, you first move your random card to the top, and then you move the top card to a random position. Unfortunately, this is completely useless. I've never seen anything come out of this formula because the BKs commute with each other, their antipodes commute with each other, but the BKs do not commute with their antipodes. Okay, I'll make a little, let me fill questions because at this point I'm getting to the actually new results. So before that, if there is anything confusing, please let me know. Okay, easier said than done. I don't actually see your camera very well, but I don't hear much.
It's okay.
Thank you. So just last year, Nadia Lafreniere came up. Okay, I'm not actually I'm not actually sure about just last year because this is when I learned it from her. She defined a new family of shuffles, so elements of the group algebra, which are called T1 up to Tn. The T does not come from transposition. I'm sorry for that. So TL is psych L, which is identity, plus psych LL plus 1, plus psych LL plus 1L plus 2, plus ... So in terms of cards, TL takes the L's card from the top and move it to a random place further down the deck. In particular, T1 is the top to random shuffle, and Tn is just the identity because there is no place further below. You can only leave the card where it is. So these shuffles are interesting, and so are their linear combinations. They're called one-sided cycle shuffles. One-sided because cards can only move further down. And they have a probabilistic meaning. So one thing that is in a way strange about these shuffles is that they do not commute. They have non-trivial commutators already for n equals 3. I mean, of course, you should not be surprised. You should be surprised that all the other families commute, not that this family does not. So in a way, you would expect it to be less well-behaved. However, that's not actually the case. And the fun thing is we know a surprising amount of things about this family, more than about, for example, the random-to-random ones. So here is, I think, our main theorem, stated in a form that maybe hides some of the essence. But so when matrices commute, they can be diagonalized simultaneously, at least if they're diagonalizable. If not, they can be trigonalized simultaneously. But trigonalized simultaneously is slightly weaker than commuting. You can have triangular matrices that don't commute. Trigonalized simultaneously is some kind of close to commute, but not there. And what we've been able to prove is that these endomorphisms, so right multiplication by all the TIs, can be trigonalized simultaneously. There is a basis of the group algebra in which right multiplication by each of the TIs acts as an upper triangular matrix. So what is this basis? Where does this all come from? Actually, we can answer the first question explicitly. What is this basis? I call it the descent-destroying basis. I don't know if this notation will make it into the final version of the paper, but here is what it is. If you have seen it, let me know. So the descents of a permutation are the numbers I, such that the permutation decreases at this number. So Wi bigger than Wi plus 1. Si is the shorthand notation for the cycle of I and I plus 1. That's known as a simple transposition or a simple reflection. And if capital I is a subset of n-1, then G of I will mean the subgroup of the symmetric group generated by the little si for I in the subset. This is known as a Young subgroup. Also, they're usually indexed a bit different. This is also the same as the Coxeter subgroup of the Coxeter group of type A. So parabolic subgroup. So for any W in Sn, you define AW to be, you take the G of the descent set of W. So so you take the subgroup generated by the simple reflections corresponding to the descents of W, and you multiply W with sigma. So in other words, you break up the word W, you see W as a word, and you break it up into maximal decreasing factors. So you draw a bar at each ascent of the permutation, and then every factor, so every piece between two bars, you can sort arbitrarily. So for example, for n equals 3, you get the elements AW look like this, where the colors are simply convenience. So the colors, I change color at every ascent, and so within every color, I can arbitrarily sort. But the colors have to stay where they are. For example, A312, I can reorder the 3 and 1, so it becomes 1 and 3, but the 2 has to stay in place because it's just a single element of its color. You should see right away, even so it takes a while to write this, to explain this in writing, that these elements AW are a basis of the group algebra, because they are triangular with respect to the usual basis. And our theorem is that in this basis, right multiplication by TL is triangular. So explicitly it says AWTL is some integer multiple of AW plus a bunch of integer multiples of smaller AVs. Now, what does...
Darij, it's Maxim Kontsevich here. In fact, it's really amazing. This summer, we have this Senior Schlossman, Leka Givetskin, Will Savin, and Richard Kenyon. We discovered many things. I didn't talk. I think we discovered exactly the same stuff and some generalization with arbitrary poset. Yeah, so
you mean for the basis or the shuffles?
Oh, no, the basis, I mean this kind of like family of elements which infinitely will be upper triangular. You said
I see. Can you give me the reference?
There's no paper yet written. I can just send you some kind of preliminary.
Oh, thank you. This would be very interesting.
Yeah, okay.
So what you get is that AWTL is a multiple of AW plus smaller AVs. Now I have not explained what I mean by smaller. There is a total order or a partial order, to be more precise. If you look at the talk very closely, you will be able to actually find this order. I'm not very explicit about it because it's not a very simple thing to define. So in particular, here is an example for n equals 4, where you just compute one possible product. You get A4312 plus smaller elements. Note that you get minus signs sometimes. This is okay. And for n equals 3, because there is only 6 permutations, I can show you all the coefficients for all of them. So right multiplication by T1 becomes this triangular matrix. And empty cells means 0, of course. And as a consequence, the eigenvalues of all these endomorphisms, as well as of all their linear combinations, are integers, as long as the lambdas are integers. So the coefficients of the linear combination. Now you can wonder, okay, how many of these eigenvalues are actually different? Here, for example, you have 3, 0, and 1. You could expect there to be 6 eigenvalues, but you have only 3. For example, the top to random shuffle, it always has only n eigenvalues. In general, you can have more, but how many more? So here is another pretty strange result. Remember that a Laconer set of integers is a set of integers that contains no two neighboring integers. So if an integer is in there, the next integer is not. And it is known that the number of Laconer subsets of bracket n minus 1 is the n plus first Fibonacci number, fn plus 1. So how do Fibonacci numbers come into play here? Well, maybe you will see at the end, but at this point, I think this should be surprising. It was surprising to us. The maximum possible number of eigenvalues, of distinct eigenvalues of this linear combination of the top to, of the somewhere to below shuffles is this Fibonacci number. Basically, there is one distinct eigenvalue for every Laconer subset of n minus 1. And in general, this eigenvalue, so sometimes this eigenvalues will coincide, but fn plus 1 is as many as it can get. And if they're all distinct, then the morphism is actually diagonalizable. But it is not, the diagonalization will depend on the lambdas. You cannot diagonalize it right away for all the lambdas, like you can triangularize it. Notice, of course, that the Fibonacci number grows exponentially, so it grows a lot slower than in factorial. This is as much asymptotics as you will see in the stalk. This is probably as much asymptotics as I know. So how can you prove something like this? Well, one obvious way, once you stop looking for a diagonalization, because as I said, it doesn't always exist, they don't commute in general. Once you stop looking for diagonalization, the obvious thing to look for is a triangularization. And if you want to do this basis-free, you can look for a filtration. Ideally, you want to filter the group algebra with a Fibonacci number of parts. So the filtration should have length fn plus 1. And on each of the quotients or subquotients, the action of RTL, so right multiplication by TL, should be just a scalar. This will give you the necessary claims. This will give you, first of all, this will show that the number of distinct eigenvalues is fn plus 1. And secondly, at least over a field, it will prove that there is a basis which makes these maps all triangular. And if the filtration is nice, which means that if all the FIs are free modules and if their subquotients are free, in that case, it's actually better than that. It's the basis exists over every ring. And yes, this filtration is nice. So I'm gonna say a few words about the filtration. I don't think it's easy to understand it just by looking at it for 10 minutes. So if I would go into the details, I would probably waste your time without really clearing much stuff up. This is one of those algebraic things where you really have to do some computations to see it. So first of all, I will define some structures for every subset of bracket n, not just for Laconer subsets, but for all subsets. So the sum of a subset I is just the sum of its elements. I hat is I, but united with 0 and n plus 1. I prime is n minus 1 without I union I minus 1. So these are the elements of n minus 1, which are not an I, but also that the next integer is not an I. So I plus 1 is also not an I. Don't ask me why. And finally, f of I is the set of all elements of the group algebra such that if you multiply them on the right by the simple transposition as I, for I in I prime, that they don't change. So in probabilistic terms, it's the Fi is the set of all random states of the deck such that if you swap the I's and I plus first cards from the top, the distribution of probabilities doesn't change as long as the cards you're swapping are not in capital I. So basically, it's about random states which are fully shuffled between certain positions, but you don't know how the distribution can change if you like move around. And finally, this is sort of crucial. If you have a subset capital I and an element L of bracket n, you denote by MIL the distance from L to the next higher element of I hat. So the smallest element of I hat that is larger than L minus L. So for example, if I is 2, 3, and n equals 5, then I hat is just 2, 3 plus 0 plus 6, 6 is n plus 1. And then you just run over the elements of n, and for each of them you see how far away is the next element of I hat. So for example, from 1 it's a distance of 1 because 2. From 2 it's a distance of 0 because 2 is already in this I hat. From 3 it's again a distance of 0 because 3 is in the set. But from 4 you have to go 2 further to get to 6 and so on. Okay, and the crucial lemma is this. If you have Q in Fi for a subset I, and you multiply it with TL, what you get is you get a scalar multiple of Q, and the scalar is actually MIL. Notice that this is a non-negative integer, which is very nice. And then you get an error term, which is in the FJs, where J has a smaller sum than I. This theorem is great. This lemma is great. This lemma already tells you that you have a filtration on whose subfactors the TL. Am I using the word subfactors correctly? No, I mean subquotients, of course. So on the subquotients of this filtration, TL acts like the scalar. The only problem is this filtration for now is given by the subsets of n. So you should expect it to have length 2 to the n, not the Fibonacci number, but a power of 2, which grows faster than the Fibonacci numbers. So the filtration is a bit too fine for us. It has some unnecessary steps. The proof of this lemma is a pretty long but also pretty straightforward case bash. Essentially, you have to argue certain properties of TL that, like, if you move things around, the total shuffle property kind of also gets preserved, except some things also move around in the shuffle. So it's written up in our preprint. You can also you can come up with it in finite time. Nothing particularly ingenious goes on in there, but in a way, all of these things work together like clockwork. So as I said, you get a filtration labeled by. You have to pick a reasonable ordering on the subsets, but the filtration has too many terms. Fortunately, it turns out that every term corresponding to a subset that is not a Laconer subset of n-1 is actually redundant. So okay, there is more notation coming up here that I probably should not explain, but basically every f of I, where I is either not Laconer or not a subset of n-1, so it contains n, every such f of I is actually contained in the sum of smaller f of j's. So the corresponding subquotient of the filtration will just be 0. You will have two parts of the filtration where the filtration doesn't change. And so you can shorten the filtration. And then you're left with only the Laconer subsets. So the length of the filtration becomes a Fibonacci number. And once you're there, the quotients actually become non-trivial, so you cannot shorten it further. And as a corollary, you get this result that the eigenvalues of an arbitrary linear combination of these TIs are the corresponding linear combination of the MILs. So for each Laconer subset, you get a corresponding eigenvalue. So so this explains why these things are triangularizable simultaneously, but what does this have to do with our descent-destroying basis? Well, it turns out the descent-destroying basis is it behaves nicely with respect to our filtration. Every term of our filtration is spanned by an appropriate subset of this basis. So, and to decide which subset, we have to define something which we call the Q index of a permutation W. So basically, to every permutation W, you associate a certain Laconer subset. And I know that some of you will say, okay, of course, it's the peak set. Strangely enough, it is not the peak set. It is another lacunar subset associated to a permutation. It is the smallest lacunar subset in a certain sense, such that the descent set of the permutation is disjoint from the set, but also contained in its non-shadow, so Qi prime. It's a complicated notion, and I don't have a particularly good intuition. I don't think Nadia has either. This is something we just discovered by, well, trying a bunch of things and seeing what works. So the K mod, this clearly yields that the parts of the filtration are free modules, and that the basis makes the matrices triangular, and it explains what this partial order is. The partial order is actually saying smaller Q index, whatever this actually means combinatorially. So yeah, this way you can also find the multiplicities of the eigenvectors. I'm not going to go into the details much. So the delta I is basically the multiplicity of that comes from the I subquotient of our filtration. And of course, if the linear combination is not generic, then some of the eigenvalues will have to be will fall together, and the multiplicities will be added. So the actual multiplicities will be sum of delta i's, but of course you understand that the delta i's are the real thing. And actually there is an explicit formula for the delta i's, which looks a lot like the Hooke length formula. It's a multinomial coefficient and choose j1 up to jp plus 1, where the j's are the intervals between the elements of the set Qi, whatever that means. So that Qi is basically a lacunar subset of n minus 1. And you take this multinomial coefficient, and you also have to multiply it with a bunch of numbers. Fun fact is that just like the Hooke length formula, this is a divisor of n factorial, which to us suggests that this should be a number of tableaus of a certain kind. Who knows, maybe it's Fibonacci tableaus. Unfortunately, none of them fully understands Fibonacci tableaus, so I will leave this as a question to anybody who does. Is there a tableau theory behind this? We don't know. So there are a few variants. One variant is that you can take the antipodes of the TIs, which means that instead of taking a random card and moving it further below, you take a random position and you move a card from further below to that position. So we call them the below to somewhere shuffles. Fortunately, the antipode is an algebra automorphism, anti-automorphism. So basically everything we know about our elements, we can conclude automatically about the antipode from algebra. We don't have to do any new combinatorics. Likewise, we can do the same thing for left multiplication instead of right multiplication. Everything is again upper triangular in the appropriate basis. Only problem is that this basis is now the dual basis, so it's a bit less explicit. All of this is pure algebra. We don't need any new combinatorics. It's one case where you get where you do a bit of combinatorics and you get one result, and then the algebra lets you copy paste this result to a few other places. So here is a stupid question that really doesn't belong into the subject maybe, and really probably shouldn't have a good answer, but I'm just wondering for the sake of completeness. So left multiplication is actually similar to right multiplication as a matrix if K is a field for general linear algebra reasons. It's not generally similar if K is not a field, but maybe it's similar for our TLs, we don't know. The computations are not amenable to computer algebra as of now. It's true for n up to 3, but that's not surprising. N equals 4, it's about two matrices of size 24 being similar. We don't know how to compute this. And the conjugation between one of those elements and their antipodes is true for fields of characteristic 0, but not for general fields. Now, here are some more interesting conjectures. So, as I said, right multiplications by those TIs are simultaneously trigonalizable. And as a consequence, their pairwise commutators are strictly upper triangular in this basis. Like every strictly upper triangular matrices, of course, they're nilpotent. But the question is, how nilpotent are they? Because naively, of course, you get something like the Fibonacci power of this is 0. Like this to the power of 2 of fn plus 1 is 0. But you know that in such situation, usually a much smaller power is enough. And here are 3 conjectures. First conjecture is actually g minus I plus 1 is enough. The second is n minus j plus 1 is enough. And the last is actually n minus j is enough if j is less than n minus 1. Of course, which of these powers will be smaller depends on I and j. And we have some partial results in this direction. We know a few equalities like this, which is pretty strange if you ask me. We don't know like why they're true, but they're just true. We could compute some of these things. And in particular, we can prove this in the case where the exponent is 2. This one we cannot prove even in that case. So there is a lot of mystery here. We have been able to check this, I think, for n up to 11. I have to say 11 is not a very large number as far as these things are concerned. I find it very well possible that these conjectures are actually false for higher numbers. It's just every bit of n factorial grows very fast. And even with all those tricks that you have with representation theory, it's not actually easy to compute those things. So this is a pretty challenging computer algebra question to even check this for n equals 12. Also, what can you say about the K subalgebra that is generated by these TIs? Well, you can compute its dimension using Sage, and you can see that the sequence is not in the OAS. Whatever this means, maybe it means that the OAS is missing a nice sequence. Maybe it means that the subalgebra is not very interesting. I don't know. The other question is, and we are currently working on it, how do the TIs act on a Specht module? We don't actually know. We have not used any little bit, we haven't used the slightest bit of representation theory so far. All of this was working in the group algebra, which is a pretty nice change from all the other families, which are usually started using representation theory. Okay, and thanks a lot, obviously, to my co-author Nadia, and also to various people who have talked to about this topic. So sorry, this thing is actually from an old paper, from an old talk. Thanks Gérard Duchamp for the invitation to this current conference. And thanks to you all for your patience.
I have a question.
Mm-hmm.
I have a question. Pencil. I would like to know whether you imagine, or maybe you know already, a possible representation of your near commutations or triangulations in terms of differential operators.
I see. You want you're wondering like what the Lie algebra generated by the TIs is, right?
Mm-hmm.
Ah, I see. Okay, I could actually try this on Sage. I don't think I have an idea of how it will look like, but it can compute the dimensions. They're probably a lot smaller than those. So yes, it's a good question. Thank you.
Maxim, no, consider, yeah. Actually, I have a lot of comments because we have, I think we have a really understanding of filtrations. They're not the basis, the filtration not compatible with the usual basis, but it works in all characteristics except 2. And the filtration are very short. It's not spread on memory, something like n square maybe. It's really very, very short. And we have complete understanding of multiplicity and so on. And in fact, we have a really huge family of matrices, kind of operators, which can simultaneously make upper triangular. Namely, you fix any descent pattern. Yeah, there are 2 to the power n minus 1 descent patterns. Yeah, for each descent pattern, we consider sum of permutation with this descent pattern.
Yes, so the descent algebra.
Yeah, you get 2 to the power n minus 1 elements. The claim will be simultaneously upper triangular.
Oh, I see.
2 to the power minus 1. It's a really huge amount of them. Yeah, and we have complete understanding of multiplicities. And to use a number of eigenvalues, it's very small. It's partition number of n at the end of the day.
Yes.
And
So, yeah.
Yeah.
Mm-hmm.
And the next thing is it's
Sorry, I have troubles hearing you. Can you repeat?
Yeah.
Okay, I still have troubles hearing you.
Yeah. Maybe I'll say what is the more general result. You consider finitely ordered post set. Yeah.
Mm-hmm.
You consider the set of all total orderings. It's some less than n factorial. If it's
okay, linear extensions. Yes.
All linear extension, and it will be indices of my matrices. And for each two linear extension, consider ratio of two permutations. Yeah. We have two orderings. The ratio will be permutation.
Yes.
And for this permutation, you get descent pattern.
Yes.
Yeah, you get something like 2 to the power n minus 1 matrices with 0 ones, corresponding to the descent pattern. And the claim that all simultaneously can be upper triangularized, and we have total understanding of this everything. I have to say, filtrations and values and so on.
I would love to see this. So my impression is that what you found probably is a better understanding of results about the descent algebra. It's well known that the descent algebra has a very large Jacobson radical. It's if you factor it out, you get the center of the group algebra. So it is 2 to the n minus 1, but once you factor it out, it's P of n. But what you did is probably you're probably doing this all characteristic free, like over the integers, or maybe characteristic not equal to 2.
Characteristic 2, maybe this only the bad one, because we have some graphics 2 by 2 matrices.
So it looks like it's a better approach to a bunch of results about the descent algebra. I would love to hear this.
Okay. I'll ask my courses, because at the end of the day, the paper is not written because we realize it follows through some obscure result about some hyperplane arrangement, which one can deduce it formally from known result. Yes.
I'm a lot more interested in the symmetric group algebra than in the hyperplane arrangements. So I would love to hear this. I think it's more like obscure results will follow from this.
So, Professor, we have one time for other questions. We just ask Darij afterwards or by Thanks.
Thank you.
Thank you.